Inductive definitions are very useful in computer science. We talk very often about algorithms defined inductively, or another word being used is recursively. And the whole idea is that you want to define some sort of a procedure or maybe some sort of a structure starting from some small ingredients and then by specifying a way to combine those ingredients to form larger and larger structures. So here is what I want to cover, how to define such inductive or if you like recursive definitions. And the way to go is like this. You will have, the aim is going to be to define a parametric property, S of n, for all natural numbers n. And you will do it in the following way. First of all, you are going to define what the property is for the initial values, or if you want, building on your terminology coming from the induction principle, this is going to be your induction base. So you will define directly what it means S of 0. Maybe sometimes you have to specify a few of them, thinking also about the second induction principle. So define the initial values, whether it's just one of them, S of 0, or maybe it's a few of them, but anyway, just a finite number of them. And then the other thing that you do is you think about this induction step, or if you want, you think about the recursion. And the point here is that for any n greater than or equal to k, you are going to define S of n plus 1 in terms of some smaller values, so up to n. And this strategy is applicable to quite a wide array of objects. You can apply this to sets, and you can apply this to numbers, or even to functions. And I want to show you a few, small examples of how this could go. So here is one example. So I'm going to have the slide. So one example I want to introduce is the factorial function. So this factorial function, I'm going to use this exclamation mark for it. It's a function that takes as arguments natural numbers, and it gives you as a value another natural number. And I'm going to define it using this idea of a recursive definition in the following way. I define it first for 0, so I will say the factorial applied to 0. This is also written sometimes as 0 factorial. Maybe this is the more familiar form of this. It's going to be defined to be equal to 1. So that's the initial value. And then I will say the factorial function applied to n plus 1, or if you want, this is also more commonly denoted like this, n plus 1 factorial, is simply equal to n plus 1 times whatever n factorial was. So this is the recursive definition. I'm defining the value of the function for n plus 1 in terms of what the value of the function was for n. So that's the essence of these recursive definitions. You define something for a larger value in terms of whatever it was for some smaller values. And for this to make sense, you have to have the direct definition given for the small values of this function. And obviously, in this case, you probably have seen this before. It's easy to prove, but I will not do it here, but it's easy to prove that this function, in fact, is exactly 1 times 2 times all the way n for all n greater than or equal to 1. And obviously, such a proof can be easily done by the induction principle. Here is another example. I'm going to define a recursive sequence. So I'm going to define a sequence of numbers, an, and this is going to be from n equals 0 to infinity, so just an infinite sequence of numbers. And I will do it in the following way. I will say, the initial, the first value in this sequence is going to be equal to 2. So a0 is 2, and all the other numbers a n plus 1 is going to be 3 times whatever the predecessor was plus 2. So again, these are good definitions. It's in the same spirit of having a recursive definition. You define the value for the n plus first term in terms of what the value was for the nth term in that sequence. And for this to make sense, to be well defined, you have to have the initial value defined directly. And in our case, I defined this a0 to be equal to 2. Here is yet another example. I'm going to define the so-called Fibonacci sequence. And this Fibonacci sequence is a sequence of numbers, and again from 0 to infinity. And the definition goes like this. I define f0 to be equal to 0, and I also define f1 to be equal to 1. And then the recursion is going to be, I define fn plus 2 to be equal to fn plus 1 plus fn for all n greater than or equal to 0. So you see, again, the same spirit. I define the terms of this sequence in terms of some values of earlier terms in this sequence. In our case, n plus 2 is the sum of the n plus first and the nth term. And for this to be well defined, I have to define the initial values. And in our case, I define f0 and f1. And so when you check this, obviously you will see that you get the familiar sequence of numbers. The first one is like we defined it 0, then the second one defined directly here is 1, and then you start applying this recursion. You say the third one by definition is the sum of the first two, so it's 0 plus 1, that's 1. Then you have 1 plus 1 is equal to 2, then you have 1 plus 2 equals to 3, 2 plus 3 equals to 5, and so on. So you see, this is you are getting the familiar sequence of Fibonacci numbers.